in a car tire and you open it up, it's going to expand kind of isotropically everywhere, and you're going to feel a very small change in the ambient pressure. These are things, this is like a hand of God coming and saying that atmosphere has to get out of my way.
So when one of those bombs does go off, where is that on this scale?
Can you go back up to that fancy chart?
Which one?
Right here. That is where TBIs from explosions in the military is measured. Yeah, so small, short, below the concussion maybe curve. Okay. So, fractures. Here's where I'm going to get really hand-wavy. Okay? I'm going to get really hand-wavy here. Mechanism of injury and stresses. Okay. I actually walked over to the Mumford Performance Center and picked up a book from Dr. Reeder, I think. The guy over at the Mumford Performance Center, and I borrow his toys all the time because he's got like infrared cams, and it's fun to bring those to class and force plate. Picked up his book on fractures when I realized I know nothing about fractures. The likelihood of a fracture depends on a ton of things. And one of them is, how is a force applied? So this is a book that says, well, I can have a penetrating, someone shoots you. I can have a crushing, someone drops something on you or you fall. I can turn sideways and snap something. I can twist and snap something. There's a lot of different types of fractures. There's a lot of different ways to get fractures. How do you apply physics to this?
Next.
Okay. I wasn't sure how much math to put in here. So the next slide I'm going to make you go over in great detail, but other than that, we'll be good. In each case, really with a fracture, so like if you're talking about injuring powers of, I don't know, like collisions, rate of momentum transfer, effectiveness of momentum transfer, peak accelerations. Turns out, sort of the same with fractures, but you cast it in a different light. We're going to talk about stresses and strains. A stress is simply the application of a force over an area. So, I can push down. If you push on a scale and you read your weight, that's the force you're applying to the scale. If you want to measure how strong you are, go to your scale and push and read off on it. If you want to measure the pressure or the stress that you're applying, you take that weight and you divide it by the surface area of your hand. So pressure is a force divided by the area it is being applied to. So you want to know what the pressure you're applying is. Measure your hand. Make sure you get your units right. So if you're reading in pounds, do this in square feet. Push. Look at the scale's reading. The scale's reading is the force you're applying. Divided by the area of your hand is the stress or pressure you're applying. What happens if I take a blob of silly putty and go like that? Do it. So push down, making sure I keep it in contact with the table. It's going to deform, right? The amount of deformation is defined as the strain. The stress is a force per unit area, and there are different ways to apply forces. I can compress, I can pull, I can shear. All forces, their application determines what kind of stress we call them. So like this is called a shearing stress, this is called a tension stress, this is called a compression stress. They all are forces applied to areas in different manners that can cause a deformation of that in a specific way. If you take a wet towel, this is a torsional stress. If you're sort of like drying out a wet towel, that's a torsional stress. So we're talking about a stress or a measure of force given to the change it creates in an object that you have it being applied to. All right. This is why I left most of the math out. When you start talking about stresses, you start talking about some scalar's one number, right? A vector, it's a set of numbers that talk about directionality and magnitudes, right? Directionality and magnitudes, how much in what direction, right? What happens if I want to apply a force like this to a cube? Don't worry about trying to understand. This is a cube. I can apply a force like this. I can apply a force like this. I can apply a force like this. I can do 3 unique types of things to each face of a cube. This force, if I make a sign change, is a pulling force. So there's a compressional and a stretching and shearing. And when you're really talking about stresses, what you need to talk about is how, for given stresses, tau and sigma, does a body respond? Does it rotate? Does it elongate? Does it compress? I'm going to stop with those now. Stresses mathematics is, this is like what comes after a vector. So people like scalars, everyone in 112 hates the beginning of my class because I do vectors, and people don't like vectors. Tensors are the next thing up from vectors. Actually, scalars and vectors are tensors, but I'll stop at that. Okay. So, if you want to talk about likelihood of bone fracture, you have to say, am I compressing something? Am I pulling something? Am I shearing something? Am I torsioning something? Am I that poor guy back in the 1500s? Big drawing quarter?
No.
No?
Yeah, 1500.
1500s? Like attaching to a horse and let all the horses go their own separate ways? People were gnar ugly back in the day. So really, each way you apply a force, this is a material. Materials have certain responses to certain stresses that depend on what type of material it is. So like if you're talking about densities of real simple material properties, the mass of an object divided by the volume it occupies, which is constant at sea level at constant pressure at a certain temperature. Bone has a response to forces applied over a certain area or stresses. Bone has material properties that depends on how you apply a force and honestly what kind of bone it is. These are measured. How are they measured? People die and donate their bodies. Or people get injured and go to a hospital. You know? If it's something like silly putty, I can sit there and I can measure my stress applied in certain ways. I can measure the deformation and I can come up with the material properties of silly putty. The data for bones is clearly less because we don't break bones to clear data. But there are multiple different ways you can mess up a bone. You can use a stress-strain idea. Shoot, I was going to bring paper clips. That's what I wanted to do, because that's a really good demo. The stress is a force applied to a unit area in a given manner. Am I going like this? Am I going like this? Am I pulling it? Am I shearing it? So there are multiple kinds of stresses. The strain is how deformed the object is for a given stress. So the way you apply a stress matters. The type of object you're applying it to matters. And you've all done Physics 111, right? No? What years are you in?
Well, she's not a bio major.
Oh!
This
Okay.
class has forensics majors.
I got you. I was like, huh. I'll see you soon. If you've seen Physics 111, there is a model for a spring that says if I apply a force, so I pull a force, the spring pulls back with the same amount of force. A spring will pull back, not with the same amount of force necessarily, but a spring will pull back linearly. So the farther I pull the spring, the harder it pulls back. The farther I pull the spring, the harder it pulls back. In a stress-strain curve, the elastic region is the region in which a spring behaves like a spring that you saw in 111, where there is a linear response, linear, for a given force applied in a given manner, and all the stress is a force applied in a given manner over an area. For a given force, if I pull, stress is pull, the object will deform linearly. For a given pull, I get a given deformation. If I double that pull, I double the deformation. There is a point, and if you go home and you play with the paper clip, go like this with a paper clip. If it's fine, it's fine, it's fine, it's fine, it's fine, and then what happens? It snaps. If you exceed the allowable amount of stress, the spring-like behavior of an object's response to a force, gone. And you reel a plastic region where the deformation stops getting bigger, commensurate to the stress, until the object breaks. If I start pulling on this, so in this case, I'm looking at elastic stresses, pulling stresses. If I start looking, no, this is, what is it? No, this is tensile, I think. I think it's a tensile, it doesn't matter. There's a region, this thing will just get longer, and then there is a region, this thing will break.
You ready?
Yeah. Okay. Here is the amount of stress you need to cause a bone fracture in a human adult cortical bone. And what is a cortical bone? I don't even know what a cortical bone is. The bone parts where you completely lose them.
Cortical bone is the hard bone. It's like it's the, what we call compact bone. So your bone's made of two kinds of bone, right? You have the compact bone that's around the edge. Think of like your mountain bike. It's hollow but strong on the outside. Then on the ends we have
Gotcha.
the trabecular bone, which is they call spongy bones. It has pieces. Okay.
Well, for that kind of bone,
Taught him something.
the bone part is, they've got a couple words for bones, and I'm like, I don't know what that means.
Yeah.
This is how much, and I'll put these numbers in somewhat context, how much force, or actually stress, how many million newtons. I said I'm exerting a force of about 700 newtons on the floor. How many million newtons per square meter you need to break a bone through tension, shearing, and compression.
What's shearing again? Two different.
Shearing would be like,
Two things. Okay.
shearing is like if a football player runs into your knee and breaks your
Because your
femur.
foot's
Yeah,
like
so
stuck,
yeah,
sort of.
yep.
Okay, got it. All right. So shear's the worst.
So how you get hit or how you get injured is going to really determine the outcome of a lot of things. But this is, so it's sort of like shearing's the weakest. You know, it's a lot easier to snap something sideways than it would be to take a bone. But this is also kind of way oversimplified.
Oh.
Like way oversimplified. It depends. Okay. So this is stress strain curves for bones. For bones.
So cancellous is the spongy bone.
Yeah, okay. I did not know what cancellous was. So cortical bones can take the most stress. But if they deform almost at all, this is how much it's deformed. You deform a bone by about 4%, 2%, 3%, it's going to snap. Tendons can take less but can be deformed more. Ligaments can take more and be deformed more. So depending on the nature, the part of the body, there's a certain amount of deformation you can take, and that results before there's a fracture. So where these lines turn over, the thing's broke. Where the line turns over, these things just broke. How high that turnover point is tells you how much force you need to stick into those things to break them.
Cartilage is pretty gnarly.
Cartilage is really weird. I think cartilage does not obey the basic stress strain ideas. It looks like it's something completely different. So like the one thing you have to be aware of with any of this physicsy stuff is you have to look at the situation under consideration and say, did my assumptions work here? Like there's a set of equations that describe the water in this cup. and how it moves under the influence of a given applied force, and it doesn't work for catch-up or blood, because those don't obey the same responses. So this is just, there's some other set of physics that I would need a lot more biology to understand.
Okay, I got it.
A lot more being almost any. All right, and it still depends. This is stress strain curves for 21-year-old, for a 65-year-old, and for an 80-year-old. And I can tell you, having just passed 40, I'm not on that one anymore. I'm like, man, my knee hurts, my feet hurt. Perspective. So just so you get an idea, a 100-kilogram person is a 220-pound person. They exert a force of 1,000 newtons on the ground, which is why I said I'm not exerting a force of 1,000 newtons on the ground. I'm like 60. The area of 2 feet, and I actually went and I measured my feet. I was like, I wonder what the thing is, so I took a ruler and measured my feet. The area of my 2 feet is about 0.03 square meters. The stress I am exerting on the ground is therefore the force divided by the area of my feet, or 33,333 pascals. Okay? If you fall from 4.5 feet, which was the threshold that the military used for their combat helmets, and you're that big, so you're 220 pounds, you will experience a collision which will change your velocity from what it was right before you hit the floor to 0 in a very short period of time. You will experience an average force of 200,000 newtons, or 6,666,000. So remember we were talking about you got up into the millions of newtons, and you start braking. This is like a ladder that I'd be painting my, I don't know, my ceiling on. If you fall in a compressive fashion, you're probably fine. If you fall sideways, you're probably going to fracture your leg.
If you fall, what's the last
Like
thing you said?
sideways.
Oh, sideways.
Yeah. You want to get like you're going into water from 30 feet high.
So if you fall like that off your ladder,
Yeah.
you'll be fine, you said?
It isn't always like, unless you're an 80-year-old woman with arthritis.
Right, okay.
Yeah.
So if you fall off the ladder and you stay straight, you'll be fine.
Well, give it a little bit of bend so that you can.
That's what I was gonna ask.
Absorb.
Yeah, you want to kind of like take some shock absorbers, let that cartilage work.
So
But
what does that do?
if you bend, then you're taking, if you don't land straight, then
Well, I
that
mean bend
takes
like
all
that.
that force on just one leg.
Yes, and then it's all, so that's a good point. If you fall on one leg, this number is going to double. Because all of that, that's a good point. If you fall on one leg, that's now like 13 million pascals, because it's the same acceleration at the same time. What bending does is it slightly elongates the time like an airbag does, and it lets you take some of that energy in things that are better suited at taking it. So, I don't know. If you fall, bend a little bit, try and go like going into the water at 30 feet. That's it. Thanks for your time.